thing's on. Hi. Great. Hi everyone. And as my previous speakers, I want to thank so much the organizers for really organizing this very transdisciplinary meeting so that we can all come together and learn from each other. So I'm Tim Lichtenberg from the University of Groningen in the Netherlands, and the work I present today is in collaboration with Matt Clement from Johns Hopkins University, Johns Hopkins. Like before, actually, everything has been set up really well so far. My talk is sort of an amalgamation of what we talked about yesterday, about exoplanets, and today to learn about the environment of the origin of life. Specifically, what we've worked on, and this was published 2 weeks ago, so you can download it already, is the question if we can test the several leading hypotheses for the ambient environment of the origin of life, specifically the impact bombardment scenario that we've heard about today already so much, using new tools, new planets that we discussed yesterday. So, the general question, of course, here is what kind of world was behaving? And Steve Mojcic just discussed actually how few evidence there really is for the first few hundred millions of years after the moon forming impact when potentially habitable conditions emerged. So essentially, we don't know if the early Earth was this kind of world that we've seen in the title slide of David Kapling's talk this morning, or if it more kind of this type of environment, very volcanically active, potentially dangerous and not extremely conducive for the types of chemical synthesis scenarios that we may want to have in this type of environment. So we've seen this slide already, this plot, specifically cyanosophilic and surficial origins scenarios have a very distinct set of requirements, which is a good thing because it makes them testable by scientific methods. And so they rely on certain chemicals in the atmosphere, certain flux of ultraviolet light at the surface, and certain redox environments in the near subsurface. But really, these things are happening in very early stages of planetary evolution, much of which is overprinted by geological evolution throughout the past 4.5 billion years ago, during the past 4.5 billion years. Now, exoplanets are a new window into that, because exoplanets give us access to planetary regimes that we do not have access to in the solar system. Steve Mojcic just outlined how the oldest rock is a bit over 4 billion years old. We're missing a large chunk that is actually the most interesting if we want to figure out the origin of life on the Earth or on early Mars. So this plot shows again a mass and radius of exoplanets that we know now. These are the exoplanets that are best constraints in their mass radius measurements. And the different isolines here show different lines of composition. What I want to specifically point your attention to is the planets that lie relatively close to this Earth-like line here, which is approximately the composition of the Earth if you scale it up in mass. Importantly, the color coding of the dots essentially gives you the day-side irradiation of these planets. Most of them are probably tidally locked, like the Moon is to the Earth. And essentially all of these dots are either purple or red. And this is a translation from day-side irradiation using conservative estimates that essentially give you the lowest, most equilibrium temperature possible on the surface of these planets. And it turns out that even if you make very conservative assumptions, then essentially all of these planets, aside from the TRAPPIST-1 planetary system, this answers a question that was posed yesterday, all of these planets that we know at the moment are either in a runaway greenhouse at present day, or have been for several millions, hundreds of millions of years, or billions of years in the past. And even a large fraction of them, even if they don't have any atmosphere, they're just melted from the strong day-side irradiation alone. That means from these planets, we can actually learn something about the very highly magmatically active phases of the earliest evolution of the Earth and Mars, and use them to perform comparative planetology on these planets by learning about their global magmatic episodes that we cannot test and probe anymore in the solar system. So this really connects to the magma ocean episode that Steve just outlined actually, starting sort of here, going through time to the long-term billion-year long evolution of a rocky planet. And the Kalos yesterday said that this is the type of plot that geophysicists like to show, so here you see my version of it. And importantly, most of the diagram is red, which indicates extremely volcanically and high melting phases of the planet, which essentially bears the secondary prebiotic atmosphere of the Earth. It goes over in this late accretionary phase that we've heard so much about. Now, importantly, the segregation, chemical differentiation of the elements, specifically redox active elements, is important to understand if we want to have a handle on the composition of the prebiotic atmosphere, because essentially the redox state of the crust in the upper mantle determine the gases that are in equilibrium with the atmosphere. So for instance, if you segregate iron to the core, you will oxidize your mantle. The same goes if you lose hydrogen to space, that will oxidize the planet. The Earth sits here, essentially since forever. Since forever we have evidence for this dogma that Kapteyn talked about this morning. And that means that the gases that come out of the Earth are mostly water and carbon dioxide and SO2. But if you would be lower in redox state, then a flurry of potential solutions become possible. One way of overcoming this problem is this impact idea that you create transiently reducing conditions for large parts of the early Hadean by using the impact of flux. And it's important here that we just, since a few years, we have evidence actually isotopically that this late accretion is probably dry and iron-rich in reducing chemical composition. Before that, actually, it was sort of a community consensus that this late veneer would be a source of volatiles to the Earth, but it turns out that this is not the case, and it's more of a source of reducing power. And in one chart, here, this gives sort of the picture, right? So we've talked about it already. You have an unproductive atmosphere in the beginning, you dump an iron-rich impactor on it, react it with ocean water, that gives you methane in the atmosphere that can then react with UV light and ultimately generate HCN and other feedstock molecules. And it was argued and posed essentially in this paper that we have heard about also this morning that this creates several windows of opportunities during the Hadean that would give us multiple episodes where the atmosphere can become productive and generate prebiotic synthesis. Now, interestingly, potentially there's a way to test this. We don't have to rely on extrapolations back in time. Potentially we can actually go and look in other planetary systems. This has been, for instance, suggested by Paul Rimmer. We could use JWST, an M-dwarf exoplanets relatively close to the Earth, using acetylene, and ethylene features to observe these things, these episodes, because the good thing about hydrogen-rich atmospheres is they have a very large scale height. So that gives us a sort of lens into these atmospheres that make it possible to analyze their composition. And it has also been suggested that Ariel may potentially do that. Now, what we have done in this, how are the prospects actually, statistically, for a space mission to actually observe these episodes and perform a test of this scenario. M stars, why M stars? Because everything is full of M stars. Now this is a plot of the stellar types in the closest vicinity to the Earth. These are essentially all stars that we have any chance of properly measuring within potentially our lifetime. And you see the orange dots here are G-type stars, solar-type stars. There are just 10 of them within 10 parsec. That means, all the blue dots are M stars. It's full of them. So the opportunity just for M stars, aside from their better transmission and emission parameters, is that there are just so many of them. So what we've asked, with a question we specifically asked is related to two mechanisms that have essentially changed the view that we have in certain types of accretion scenarios in the solar system to exoplanetary systems. We asked the question, how will these two mechanisms affect the composition and time scales of impact bombardment in these systems so that we can actually gain a statistical understanding if there's a possibility that we can probe these transiently reducing atmospheres. In the left-hand side is a mechanism that is really emerging in the last few years, let's say last 10 years, in the early solar system accretion geochemistry community, that large parts of the bodies that we see today are not like asteroids and meteorite parent bodies, are not pristine samples, but they're highly processed samples of prior episodes of planetesimal formation, collision, and re-accretion. And that means that essentially all the meteorites that we have must be understood through the lens of their geophysical evolution, that is specifically in the first few million years of the solar system, driven by the decay of short-lived radioactive isotopes, and importantly aluminum-26, which is a half-life time of 700,000 years. And this isotope leads to a volatile-rich body degassing most of its amplified elements, and then the onset of melting and the formation of magma oceans, specifically in the earliest phases of the solar system accretion. But it leads to loss of highly volatile elements and even moderately volatile elements, even on the seemingly most pristine samples that we have at present day. And then there's a second mechanism that we probe here, and someone from the audience asked this question, I like this term, so I came up with it again. Actually, the bright young star paradox, there's something like that. It is the point that M stars undergo a very extended pre-luminous, very luminous pre-main sequence phase that essentially pushes the habitable zone for several hundred years outwards and lets them lose their water content, the planets in these potentially habitable zones later on. This was discussed by Rory Barnes yesterday, showing here in red the stellar types that are most prone to extensive water loss during this phase are the lowest low mass stars, the M groups. So what we did then is we performed M-body simulations. That was explained in general how this works yesterday as well. We ran a suite of M-body simulations for different types of host stars, including community standards of assumptions of the initial planetesimal disks. We performed bombardment statistics on this. So we basically varied the composition of the initial disk of the planetesimals and of the protoplanets based on certain calculations and theoretical models that are based on the literature, how much water content and therefore oxidizing power these planetesimals deliver. The same goes for protoplanets. The disk that we use is subdivided into three regions, one on the inside of the runaway greenhouse threshold, one outside of it, and inside the water snow line, and region 3 is outside the water snow. Now, first of all, the time scale of bombardment, because it's important to understand how long these stars may be active in producing these transiently reducing phases. To cut it all short, no impact will fall onto potentially habitable planets at all in M-star planetary systems. And that is because the impacts decline exponentially over time, and when they have stopped completely, the M-star planets are still in their magma ocean phase. This is shown on the left-hand side, so this is the cumulative mass fraction of reduced impacts, potentially reduced impacts that fall onto M-star habitable zone planets. This is time. This is for a 0.08 mass star, 0.12, 0.4, and this is a solar analog. This is essentially a solar system reference scenario that reproduces the solar system. The black curves are the impact bombardment, cumulative over time. And you see that these curves go to later ages with increasing stellar mass. But at the same time, this orange line, which is the transition to the main sequence for a given stellar mass, goes to the left with decreasing goes to the right with decreasing stellar mass. So it's anti-correlated with the stellar mass. And that means for this case, and this case, no impact at all falls once the planet is solidified. That means all impacts fall into the magma ocean. The mechanism just cannot work in M-star planetary systems. So only G-stars can receive any later-producing power potentially, but it's also very dependent on the composition of these impactors. For instance, the ratio of iron to water that is delivered with these impactors. And so this is essentially like a selected from me now selected subsystems, submodels to explain you the main concept. We ran many models. There are three cases. A comet-like one that is essentially motivated by cosmochemical abundance of elements. It assumes no geophysical processing in planetesimals and in protoplanets, so no magma ocean water loss. And then when we do compare the water mass fraction that is delivered from these late bombardment episodes between solar-type stars and for different masses of M stars, then we see that they receive orders of magnitude more water than the Earth has at present day. It's not completely not visible here. The Earth sits about 0.18%. If only protoplanets dehydrate as much as they can due to published literature values of protoplanet desiccation in the magma ocean phase, then things become somewhat better, but still both G-star systems and M-star systems receive several orders more water than the inner solar system did. Only when planetesimals significantly dehydrate and lose their water content due to internal processing, G-stars and M-star systems can reach values of water delivery that are comparable to the inner solar system. Now, that means the overabundance of water that is delivered just by late accretion alone is several orders of magnitude higher than any escape mechanism can deplete. We're talking about something on the order of 1,000 oceans relative to loss values of at maximum tens of oceans to maybe 100 oceans. That suggests that M-dwarf planets in the habitable zone very likely have large extended volatile envelopes. We tested this with a variety of parameters, and you now have to believe me, but all but the most desiccated systems are significantly over-enriched in volatiles and therefore oxidizing power relative to the planetesimal dehydration scenario. To bring this in context, we heard a lot about the system, so I want to also come up with my own version here. This is from the Agau paper that was cited yesterday. And TRAPPIST-1 is actually evidence at this present time for volatile enriched planets. And this can be seen in this plot here. So this is the periods of the TRAPPIST-1 planets, this is the semi-major axis, this is their water mass fraction. The Earth is about here. This is BCD, and they are indeed very dry. They are inside the runaway greenhouse threshold. And this is EFGH. And the different colors are different iron mass fractions because iron mass fraction and water content are somewhat degenerate with respect to each other. The value of the Earth is 32.8%. And if you assume that as an initial guess, then the current most consistent value with the measurements is about 5 to 10% of water in these planets. And if you are still not convinced about very volatile enriched envelopes around low mass planets in these planetary systems, then just about 4 weeks ago, Luc Payet and Science, they refined the measurements of the M-dwarf planets that we know best actually, such that we can distinguish in a mass radius plot between the Earth-like line and the 50% water line. And you see now that there is evidence for a population specifically around M-stars that is extremely volatile rich, essentially close to the cosmochemical value, which suggests that these planetary systems form without any initial planetesimal dehydration mechanisms like the solar system has experienced early in its history. And this essentially brings me to the end of my talk. So only the driest of starting conditions produce anything close to Earth-like values. M-star, M-dwarf planets are significantly volatile over-enriched relative to the solar system. That means they are so strongly over-enriched in atmophiles that secondary atmosphere are not only a possibility, but likely massive volatile envelopes. Late-stage impact bombardment in M-dwarf systems is swallowed by the magma ocean, and it means only G-star planets can probably experience late-stage bombardment, like we have heard about this morning. Thank you so much for your time.
Very cool models. I'm particularly interested in your late stage impact bombardment models and your conclusion that M-dwarfs won't be able to get any late stage reducing power. I wonder if you tested the kind of cutoff point, like can K-stars, for instance, potentially get some late stage reducing power?
Yeah, it's a linear function with stellar mass. So the more mass you get in principle, according of course to the settings we have used in these models, so more massive stars should in principle, just because there's more mass around, because dynamical timescales are longer, so like higher mass stars should receive some fraction of late stage impact bombardment. Yeah.
And I was also wondering, I've seen some magma ocean cooling models that show extremely efficient cooling as quick as 10,000 years even. I wonder what your thoughts are about models like this and what the differences are between your models and these, if you've heard of them.
Well, we didn't run any magma ocean models here, but just in general. So in order to cool, there's a discussion in the community. If you're inside the runaway greenhouse threshold, which is about 280 watts per square meter, globally averaged insolation, then you can only cool if you have no water anymore and also no hydrogen, because those are very strong greenhouse gases and you need to deplete these volatiles. So if you accrete a planet completely without volatiles, then you can do that. But as I essentially showed, that there's increasing evidence that all planets initially create very volatile rich and essentially need to go through a desiccation or dehydration phase in order to arrive at somewhere close to Earth-like values. So within this context, or within this assumption, all planets inside the runaway greenhouse threshold, and for M stars this is up to 1 billion years essentially for a TRAPPIST-1-like system, they will essentially stay in there until they deplete all their greenhouse inventory, either hydrogen gas or H2O, essentially. Yeah.
Here, I have another question here.
Paul Rimmer, University of Cambridge. Very, very interesting talk with some fairly, it looks like fairly pessimistic conclusions about planets around M-dwarfs. If they have these large envelopes, it's going to be hard to have temperate conditions on the surface, I would imagine, and it's going to be hard to really get this reducing power from these late impacts. What do you think is the most promising scenario for M-dwarfs, or you can't conceive a way of getting this kind of chemistry working?
No, you're right. It's from that point of view, it's fairly pessimistic. I'm not sure if this is a pessimistic answer in general. Maybe the answer is just simply that M-dwarf planetary systems are just not conducive for life as we know it. But in fact, we can do it. We need extremely strong radioactive content. Not extremely strong. Solar system-like is okay. If solar system-like works, and the mechanism of accretion is not strongly dominated by so-called pebble accretion, then potentially M-dwarf planetary systems can reach these values. We need those two things to work. No massive volatile delivery via small grains like pebbles, and at least solar system-like levels of aluminum-26 and other short-lived radioactive isotopes. And then I think you can essentially desiccate these planets strong enough that you may end up with something close to Earth-like conditions. Yeah.
Thanks. We have another question out here.
Hi. So, some years ago, Jack Lissau wrote a paper where he argued that M-dwarf planets would be subject to a lot of impact erosion, and the basic idea is that because you're close to your parent star, there's a high Keplerian velocity, so the velocity of the impact and the energy is a lot greater. So, when you have your early impacts, are you just assuming that all the volatiles get delivery, or is there a possibility that some of them actually could be lost by impact erosion?
Yeah, no, you're absolutely right. In this context, we don't basically include there's no impact erosion. What I wanted to say here, that these mechanisms in the solar system, not just Jack Lissau has written papers on this, but many others, show essentially that this mechanism in general is a very strong function of the composition of the impactors. And on average, impactors deliver more than they basically erode. And the differences that we calculate, that I calculate, for instance, from different planetesimal evolution scenarios, and others calculate too, if you take a step back from what we see as late accretion specifically in the solar system, because of how accretion has worked out specifically for us, then from combining like cosmo or astrochemistry with a general view of this desiccation mechanism tells you essentially that you need very strong depletion to go down to levels that the composition then allows for impact erosion. So my view of this is that, and like others have shown this, for instance, for the case of Venus, that impact erosion can work, but it's a minor component of the overall picture.
Okay, one more question? We got that.
We have to be cautious because we don't know the composition of M stars very well. So we don't know we also do not know, although there's a weak correlation between disk mass and stellar class. It seems that a stellar class goes from M to F or A, that disk mass tends to go up. So we don't know the initial disk mass. We also don't know, if we don't know the composition, we don't know the disk mass, then it's also difficult for us to say, okay, what could be the reducing power? So what is the fraction of metals to silicates, for instance, that would be in the source region? So it seems to me that to make good progress here, we have to have a better handle on the composition of the system, the minimum mass of the disk, whether planet migration has taken place, which of course stirs up velocities and leads to bombardments and late accretion. And I'd just like to have your comments and foresight on
I
steps that
absolutely agree
need to
with
be
you.
taken.
I absolutely agree, fully agree with you. And honestly, this is exactly the attempt to do that, right? I basically want to step away from the assumption that is usually done that you use initial conditions like we see them today after 4.5 billion years of reprocessing and use them as essentially the gold standard for everything. So we need to relax those conditions and inform them by the physics and chemistry that we know works in the ISM and during planetary formation. This is the result we get at the moment. I just want to point out, I see what you're saying, but literally we have now increasing number of planets that say that M-dwarf planets are extremely volatile rich. There's very little chance to explain these planets, this is just 7, it will increase. There's very little chance to explain them with anything else. I think maybe there's definitely some wiggle room here, but you will, with an iron variations in iron depletion or enrichment, you will never go anywhere here. The hydrogen line here, for instance, shows you that if you want to be, use as much parameters as possible, then you cannot fit those planets with a hydrogen component. So at the moment, the simplest explanation is that actually, specifically in M-star systems, it's not a radius value, but it's a triplet. 3 peaks in composition where M-stars particularly fill the extremely water-enriched part. No. I agree with you. We need to work more on this.
Okay, thank you, Tim. Let's give him a hand. And next I'd like